Similarly, we can look at the probability that at least one of the intervals we create fails to cover the true value. So you can see here, if we have only one interval, the probability it fails to cover the true value is 0.05, and that's by construction. If we make a 95% interval, we expect it'll cover the true value with 95% probability. And you can see, as we increase the number of independent intervals we create, the probability that at least one of them fails to cover the true value increases pretty quickly. So why is this important when you read reports of scientific finding? What's going on here? So when you read papers that have been published in scientific journals, those are only the papers that have been accepted out of many, many that have been submitted. And even the papers that have been submitted are only a subset of the projects that people have worked on. So what happens? Which of the papers, which of the projects that are chosen for publication? The ones with the most interesting results, typically. This problem is called publication bias. In other words, imagine that there are 100 studies conducted and all the null hypotheses are true. There's nothing going on in any of these studies. But if everyone does a test that accidentally rejects the null hypothesis with 5% probability, 5 of those 100 tests should improperly or incorrectly reject the null by accident. And the publication bias problem is that those 5 studies out of the 100 are the most likely to be published because they're the ones that claim to have found some new results, have discovered something. So the problem of publication bias is that the papers most likely to be published are the ones that are likely to have accidentally rejected the null. And that's why it's very important to have replication studies for people to try to reproduce results that have been published.